1, 2, 1, 1, 1.
So let me invite the next speaker, Eugene, and let's find out what he will be talking about the out of kernel models.
So, my name is Eugene Syromiatnikov, and I would like to talk a bit about out-of-tree kernel models. It just happened so that I interacted with out-of-tree kernel models for quite a long time, and I think that this topic is pretty undercovered. Well, for a reason. So I decided to share some of my ideas and my practices of how it works. Basically, if you already know how to build out-of-tree kernel models, then this talk will be pretty much useless to you. And it's a good time to decide that you want to move somewhere else, but still. Otherwise, I think it's more or less basics, but yeah. Okay, what out-of-tree kernel models are and why do they are needed? So Linux is has a monolithic modular architecture and supports loading of modules, pieces of code that can hook up into various places of the kernel and be used on the running kernel. So usually kernel models are bundled with the kernel itself and maintained along with the kernel. But sometimes there is a need to build kernel model out of which is not included in the kernel tree. And I would say that the two main reasons for that. First and more popular reason is porting of some in kernel driver to a different kernel version, like backporting or forward porting. Backporting case is more common because usually you want to have some new shiny driver on your old rusty kernel, well, okay, stable kernel, let's say, and you just try to build it against this old kernel. Otherwise, the other case is forward porting. It's less common, but it still has its place because sometimes code is deprecated inside kernel and removed because it's unmaintained, and sometimes happens that you get the hardware, the driver for which is already removed from the kernel, but he had been supported at some point, so you have to forward port a driver for this hardware to the newer kernel version. Or, for example, if you have some externally developed models, then either there will some piece of code which is called Linux driver for Linux, and which you found on some FTP site that worked for some old kernel version, and you still have to port it. Or there are some actively maintained projects like some networking drivers. Well, it's most common case because usually hardware vendors release schedule sort of differs from kernel's release schedule, and they're not always possible to merge everything in the main line, and usually vendors want to support various distributions. Well, so there are reasons for that. There are reasons for them to provide out-of-tree models that support their hardware. Another popular case is various file systems, especially distributed file systems. For example, Lustre, but well, Lustre is not a good example because the server part that implements that changes kernel's file system locking mechanism, basically implementing distributed locks, changes kernel itself, and it can't be distributed as a simple model. And the client, and the Lustre client is upstreamed some time ago. So yeah, there are some more or less obscure file systems that can be mainlined for some reasons, either due to discrepancies in license or unwillingness of some people to put it mainstream. Well, there are usually reasons. So, regarding driver development itself, unfortunately, it's a topic that very poorly covered. There is a book that's called Linux Device Drivers, and it does a pretty good job of describing how to develop kernel drivers for Linux, especially for the fact that it describes it for the Linux kernel version 2.6.10, which has been released in 2004. So, and yeah, there are no plans for the new edition for some reason, and one significant reason is that the pace of development of the Linux kernel is too high, and by the time any new book has been released, it will be already obsolete. So yeah, the authors kind of hesitant to try to release a new version. So the only actual reference which is relevant is Linux kernel itself, and basically the only thing you can do is to read the kernel's code and try to figure out what to do. So porting of kernel drivers is a bit different in terms that you don't have to be a experienced kernel developer in order to port a driver. You just have to be able to run a compiler and see what errors it produced, and then fix them and try again. Because Linux doesn't have any stable API, and it intentionally doesn't have it. But luckily, most of the changes in API are pretty visible in terms of producing erroneous, in terms of issuing compiler errors. So usually if API has changed, then all the users of the old API just stop working, stop compiling, stop building. So basically there's no magic in backporting. Usually it's more or less mundane manual work when you try to fix some errors that then produce good compiling, and just dig into the kernel history and try to follow changes in Linux API in order to know in advance what has been changed. So it helps you a bit. And I would say that there's no special tooling for that that could assist it, especially except for some projects that do exist and try to solve exactly this problem, like how to assist the backporting process. But I would say they're not really helpful for experienced backporter. But on the other hand, they could be quite useful for those who doesn't regularly do some backports of drivers. So if we look at the porting of kernel models from the point of view of independent developers, there is a significant issue that is supporting for multiple kernel versions, because, well, if you have divergent trees, then you don't have to do that. And if you have diver out of trees, then, well, you basically have to support everything. So how it could be done? Well, there are some macros present in the Linux kernel that allow figuring out what version of kernel is, and by trying to compare the version you're built against with the version, you know, some feature is introduced, you can construct some if-defs that could work, but in fact, in reality, they are mostly useless, because there are a lot of users of non-mainstream kernels. Basically, every distribution has some patches, and some more stable distributions have much more patches, and it's not uncommon to have some new APIs, new subsystems being backported from the newer mainline version while keeping the reported version of the kernel the same. So yeah, if you try to support these distributions, these macros are mostly useless to you. So we're reverting back to the good old configure macros. So there are several projects that aim supporting of vast majority of Linux distributions and various kernel versions, and they maintain some set of macros after conf macros written in M4 that helps them detecting availability of various kernel features or differences of different variants of API, or this kind of stuff. One example is ZFS on Linux. As you can see, basically, these macros are pretty simple. They try to compile some code snippet, and if it works, then they execute one argument, and if they usually it sets up some afterconf variable, and if they don't, they execute another branch. Well, pretty simple and pretty common for afterconf macros. And there is an example of detecting amount of arguments for the sget. So yeah, I think that it pretty much says for itself. But the first thing I don't like in ZFS on Linux is that its macros are pretty simple. And the second one is its license. So there is another project. Unfortunately, it ceased to exist, more or less, and not maintained. It's not maintained anymore. It's Berkeley's laboratory checkpoint restore, and it aimed to provide checkpoint restore functionality for applications that run on high-performance computer systems. So if you have some parallel program, MPI program, that runs on a set of nodes on a cluster, and you want to checkpoint and restore it, then you would have this. You could use this project that implemented some in-kernel checkpoint restore functionality, and then there were some hooks in various MPI implementations. I believe it was OpenMPI and Peach. Yeah, it was in Peach mostly. Then make use of them. But anyway, the first thing is, yeah, that project is GPL licensed, and second one is it has much more useful macro repository, like like you have a specific macro that checks for amount of kernel amount of arguments used in the specific Linux API function. And you can check for kernel symbol, for structural attributes, all this kind of stuff. And they have a waste library of such macros. But yeah, if you don't really like writing M4 scripts and writing thousands of code of configure scripts is not your thing, you can try to skip for something more simple and try to write some Makefile magic. It's from QLogic drivers Makefile that tries to do, well, roughly the same thing. Add some definitions based on, well, some observations. Basically, they try to grab for the presence of some symbols, of some definitions in Linux headers, and based on that they define various preprocessor definitions. You can skip even that and try to battle with discrepancies of APIs in source code itself by performing some if-def trickery and stuff. So I have some examples of that, but that approach is pretty much limited because, for example, you can't overcome, for example, the difference in amount of function parameters that way. So, yeah, and yet another approach, and do nothing because you don't care about supporting multiple definitions. Well, I'm not exactly correct in respect to Riser4. They have a kind of different kind of development approach because they aim for merging the code into mainline, and basically what they do is they prepare a patch for each kernel version. So basically their release looks like patch that you apply to the mainline tree and can use. But on the other hand, it's a good way to go if you if you see that your code will be released, will be merged to the mainline kernel at some point in time. But for the actual users of your driver, it's not very it's not very useful way for distributing your driver because, well, in fact, the patch does very little changes outside the driver itself. It basically exports to a couple of functions, and that's all. So there's no real reason for them to distribute it that way. They just complicate a bit out of the packaging of the driver. But yeah, they're developers, so they decide how to distribute there. So once we finished with backporting and made the thing compile, we're moving more or less to building. Kernel sort of supports building of out-of-tree models, so you can point at some directory where models reside, and it happily builds models inside it. And yeah, here's an example how to do it. But you don't expect any more, and you can't expect any more than that from the kernel. For example, kbuild, the kernel's build system doesn't goes well with out-of-tree building. So, for example, when you like to have your build artifact outside your source tree, and usually you have Makefile that is processed by configure after make and will be put in the build directory along with other build artifacts. And kbuild just doesn't support it in any way. It has some support for out-of-tree build, but it can't pick up Makefile from the build directory. Another particular things that I'd like to mention is that kernel is, since kernel parses the model as it loads, and it has some assumptions regarding the layout of the model. And this layout can easily be broken with the changes of the GCC version. So, you have to build your models with a version of GCC that the same as the compiler that builds the kernel you're building your model against. So basically, you have little idea, with which compiler has your kernel built. So usually distributions patch kbuild a bit in order to either have, they have to compiler specify it explicitly one way or another. So it's not simply GCC plus some version or something like that. And but yeah, it's not all of them do that thing. So if you see that some strange thing happen when you try to load the model, or when you don't expect them to be, it's probably a good idea to check that your version is the same as the kernel's one, especially if you build for SUSE. Yep. So this is an example of Makefile. One particular interesting thing here is that this Makefile usually read twice. For example, usually you have Makefile for actually calling some targets, like default target all or modules, or this kind of stuff. But then, when you call kernel for building the models, kbuild reads this Makefile again in order to get a list of objects to build and list of kernel objects to generate. So it's a thing that you want usually to remember, because otherwise you you could have your out-of-tree build broken, for example. And when we finally build our package and want build our kernel model and want to distribute it, we go to packaging. And that where basically all is much worse, because, for example, some distributions just ignore the existence of out-of-tree modules. And you have no official policy how to package them. You have no, good practices on packaging them. So they're only bad examples of packaging kernel models. Others, like Debian, do have some examples, and in fact, they have more or less good integration with existing tools for supporting packaging of out-of-tree models. One of these tools, and well, de facto the only tool that exists, is dkms. dkms is driver kernel module support, if I remember correctly, is a set of bash scripts initially developed by Dell somewhere around 2003, 2004, that provides an infrastructure for managing of out-of-tree models. It supports full cycle of management, starting from building, from installing, up to packaging in various formats. It can produce Debian packages, it can produce RPMs, it can produce Red Hat driver disks, it can produce SUSE's kernel module packages. So basically, the only thing you need in order to work with out-of-tree kernel models and manage them. So dkms maintains its own repository for out-of-tree kernel models, and in order to work with out-of-tree kernel model using dkms, you have first to add it, and then you can build it and then install it, basically, with the appearance of some new kernel with a different version. Those models that have specific flag set, for example, auto install, will be automatically rebuilt and automatically installed into this new kernel version. If the distributions, if the distribution implemented the hooks into its kernel package. But for example, Debian does it. So that's an example of dkms configuration script for some kernel drivers that consist of two modules. Since dkms itself is written in bash, dkms-conf is also just a bash script that's included by dkms script. And what could I say? You can easily perform anything you want in terms of testing the environment, performing some configuration and stuff if you have to, because in order to align with other part of your built infrastructure. I would say that more or less it's self-descripting, except probably while most of the arrays that defined is this configuration per kernel module, make is an array that is defined for various patterns of kernel versions, and that what usually baffles people unless they read the documentation. Otherwise, it's pretty much simple. But while dkms is more or less de facto standard, it's not perfect because it assumes that when you package your kernel module with dkms, dkms is the only tool you're using in your build infrastructure. And as I already mentioned, you can probably want to use autotools. You could probably want to use some way, use your own makefiles in order to build kernel models. So the way your kernel model is built under dkms became a bit convoluted. So in the end, you have a makefile that is embedded by kbuild, as we've noted previously, that has rules that calling dkms building and among other things. And dkms uses config that calls make with this makefile spec. And if you want to build package, that probably you have dkms some target in your makefile that builds dkms, calls dkms for building npm package or debian package, and dkms includes your makefile back, and that's where things can become a little tricky because of the way it works. So the other thing is that dkms implements full model management functionality, and as with other package managements, as for example the ones present in Ruby and Python, well, it usually conflicts there with the in-distribution package management facilities. For example, well, again, Debian has pretty elaborate scripts for integrating with dkms, and still it doesn't work well in every time. So akmods is another approach, more popular in, well, more accustomed in RPM-based distributions. Basically, it's a set of scripts for rebuilding kmod SRPMs for various models. So if you have a kmod RPM, it's basically an RPM that includes kmod source RPM along with a bunch of shell scripts that make it work. And the spec file for this akmods is just horrible because, well, as it's usually used with RPM-based distribution, and well, one of the most popular RPM distributions is Fedora, and it doesn't have any guidelines. Its spec file is just unguided. It's supported by some side project, some side projects that provide them, and basically it's a boilerplate written around huge kernel model package RPM macro. It's one of biggest macros present in RPM macro repository, and kernel model package itself is a wrapper for the kmod2 shell script that in turn generates parts of RPM specs for various kernel versions. Yeah, it works around this way. And it's pretty much unmaintainable and undebuggable because, well, the spec basically generates during the build time, and, well, you can't debug it well. So another tool I would like to mention is the ddiskit. The ddiskit is kernel model backporting assistance tool, which is tailored for building Red Hat driver disks and workflow associated with it. So initially, it was just a set of Makefile rules for generating, for building kmods for a set of kernel versions. Then the second version was made by Jan Masters, and it did more or less the same, but instead generated RPMs, kmod RPMs, and now there is a third iteration which does nearly the same, but it's now written in Python instead of Makefile, and has a bit more automation. And yes, the spec files generated by ddiskit do not use kernel module package. So there is an example of its usage. Basically, you import some driver you export some driver from the kernel source tree. Then you can perform the actual backporting. The ddiskit has some integration with Kilt, one of popular page management infrastructures, and then you can build RPM that this command just automatically will automatically generate spec file and tries to build the package inside mock. It has integration with mock now. And in order to generate driver disk ISO, there is another command available, which also can optionally check GPG signatures in case you have your RPM package assigned and want that to be checked. So that's it. Thank you for your attention. Basically, this is probably most useful slide. The links to all the projects I've mentioned, and if you have any questions, I can answer them. Yes.
Since you mentioned Riser 4, is that still the plan for the developers to integrate it in the mainline kernel? Because the latest information I got from the network, actually the last year, that there are no plans.
The question is about Riser 4, yes? Yes, the question is about whether the Riser 4 developers still plan to integrate their driver into the mainline. Well, I have no idea, because, well, I looked at Riser 4 drivers some time ago, like 2 or 3 years ago, and at that moment there were plans, but, well, they still distribute their driver the same way. Well, I've checked like yesterday, and the latest package is still in the patch format. And I've looked at it, and it still has like some minor patches outside Riser 4 directory and then the driver itself. You can easily repackage it in order to be the proper out-of-tree drivers that can use dkms or something, but yeah, they still maintain it that way, probably because, well, they have this development workflow. Oh, thank you. Oh, sorry. Yeah.